Now we're going to get to lecture 13, which is another lecture based on chapter 5, the second law of thermodynamics. What we will see now is how we can use what we learned to define an absolute temperature scale. We will derive equations for the maximum possible performance of cycles operating between two thermal baths, two thermal reservoirs, and then we will show you what exactly these cycles are. They're called Carnot cycles. We'll show you Carnot cycles for power and Carnot cycles for refrigeration. So let's review what we had last time. We learned that all internally reversible power cycles operating between the same thermal reservoirs, a hot one and a cold one, have the same efficiency. So no matter what the reservoirs, all the reversible heat pumping cycles between the same reservoirs also have the same coefficient of performance. So the properties that determine this is not a function of the cycle itself. It doesn't matter what the cycle is, nor does it matter what the fluid is that it is worked on. The property that determines this is some mysterious characteristic of the heat reservoirs, which is where I left it last time, so that the efficiencies, which are functions of the ratio of the heat that goes into the cold side and the heat that goes in the hot side in a reversible cycle, has to be a function only of this mysterious quantity theta for cold and hot. All right, so far, so good. What is that quantity theta? Well, that is the postulate. It's Lord Kelvin who postulated that this mysterious quantity theta was actually the absolute temperature, the temperature on an absolute scale. So he postulates that then QC over QH is in fact the ratio of theta C over theta H. So the postulate comes in two parts. One, that the mysterious theta is actually the temperature in Kelvin, in absolute Kelvin, and that the mysterious function is simply a division. Again, this is something that comes of the fact that it fitted the known experiments at his time. So we're now here with the ratio of the heat that goes into the cold side to the heat that goes into the hot side in a reversible cycle is the ratio of the temperature of the cold side over the hot side in absolute values. This works for all cycles. Now, if a reversible power cycle were operated in reverse direction, it would be a heat pumping cycle. In other words, the W for the power cycle would, the W out for the power cycle would be the W in for the heat cycle. Then the magnitudes of QH and QC would also remain the same, but their signs would be opposite. Now, what is this mysterious absolute scale? Because you see these ratios depend, of course, on the zero given for T hot and Tc. The ratio in degrees centigrade would not be the same as the ratio in degrees Rankine or degrees Kelvin or degrees, well, the ratio in degrees Rankine and Kelvin is the same, but in centigrade or Fahrenheit it's not the same. So we have to find a zero. Well, what they did, it's again an observation by Lord Kelvin, is they make a reversible machine that operates at the temperature T and draws a heat Q from outside. Well, they operate this material at the triple point of water, which is a well-defined temperature. It doesn't depend on pressure, it's a triple point. And they observe that this machine draws an amount of heat QTI. So Q for the triple point of water. And then they notice that the temperature of a machine that operates at that the heat of a machine that operates at another temperature scales vis-a-vis the heat that goes into a machine that operates at the triple point of water as T is 273 Q over QTI. So this now, if you feed this back into that equation, it tells you that that equation will hold if you refer any T to 273.16, which is, of course, a value that's below the triple point of water at atmospheric pressure. So that's that defines the Kelvin scale in practice vis-a-vis various triple points. So there's a whole article on how you define the temperature scale. So it's an optimization between, or a trade-off between the triple point of hydrogen, neon, argon, water, gold, copper, and so on. But the bottom line is, this number is what sets your temperature in absolute Kelvin. And if one were to do the same experiment, the exact same experiment with Fahrenheit, one would get here the conversion factor between Fahrenheit and Rankine. Okay, so that sets your absolute temperature scale. Now that we have that temperature scale, we can find, for a reversible power cycle operating between two reservoirs, what the efficiency is. And you know that the efficiency of the reversible cycle is the maximum possible efficiency for that system. Well, you know it was 1 minus QC over Q hot for the reversible cycle. So we know that this is like that. And therefore we know that the maximum efficiency is 1 minus TC over T hot. This is a function that you must remember. It is a Carnot efficiency. It is the maximum possible efficiency of any thermodynamic cycle operating between a source at a temperature T hot and a source at a temperature T cold in absolute Kelvin. You must remember this. I will ask. Now, if we apply the same thing for a heat pumping cycle, and we look at the coefficient of performance in cooling, which is the amount of cooling heat that you get for the amount of work that you put in, it's QC over Q hot minus QC. You operate the same little transformation of variable, and you know that beta max, the maximum coefficient of performance in cooling, is TC over T hot minus TC. If you operate the same cycle as a heat pump, the useful heat is the hot heat now. The cycle is what you put in, so the efficiency, or the coefficient of performance really, is Q hot over Q hot minus QC, and that can be worked out using this relation to be T hot over T hot minus TC. So the very first conclusion that you get for this is that you will get the maximum efficiency out of any thermodynamic machine if you make the difference between the hot side and the cold side as large as you can. So eta is the efficiency as a function of the hot side temperature for a fixed cold side temperature at 298 centigrade. You can see that eta increases and tends asymptotically to 1 as you get to very high temperatures. Now, conversely, if you want to optimize the efficiency of a heat pumping cycle or a refrigerator, you want to run that refrigerator over as small a temperature difference as possible, because that makes your denominator small and that makes your beta large. So the best power generation cycle is one that runs at the hottest possible temperature. The best cooling cycle is the ones that runs as the lowest possible temperature gradient that you want to achieve, temperature difference that you want to achieve. Now, let's define these quantities a little bit further, and we're going to get now to the notion of entropy. So let's take one of our internally reversible cycles, which I have here, and let's take a little step through that cycle so that you change the heat by a certain amount, delta Q. You change that heat across the boundary of your system. So you have heat removed or heat added at the temperature TB of that boundary. We're going to be very careful that we have to distinguish between heat and entropy exchanged at the boundary of the system or eventually produced inside the system. But for the moment, we only look at the heat at the boundary. Now, the system is reversible. It is tending to equilibrium at the end. So basically, the temperature is the same everywhere. It's a quasi-equilibrium. Now, in one step, you evaluate, on each step between here and here, you evaluate the quantity delta QB over TB, right? And then you integrate that over the entire cycle. So the integral over the entire cycle is this integral with a circle in it of delta QB over TB. And really, the B is not superfluous in what we're going to be doing. Just remember, it is the heat that goes across the boundary. Now, from chapter 6, from either the Kelvin or the Clausius formulation of the second principle, we will derive for you that for internally reversible cycle, this is 0. But for irreversible cycles, this has to be smaller than 0, which then leads us to a concept of thermodynamics that is a Clausius inequality for any practical cycle, which is not completely reversible, which has irreversibilities. We have to have that this integral over the boundary of the ratio of the heat. No, the integral over the whole cycle of the ratio of the heat that crosses the boundary over the temperature of the boundary must be negative. From here on, I will drop the index boundary because it's understood that all heat exchanges are happening across the boundary. Now, let's take a look at one of these internal reversible cycles and use this Clausius inequality. Well, so if I have a cycle where I go from 1 to 2 across the reversible path, reversible cycle, I will have between 1 and 2 a change in the quantity delta Q over T, which will be S2 minus S1 from here to here. Because I know, and I will show you later, that this ratio is a state property. So if the cycle is reversible, that value of the state property is S2 minus S1. If I come back from 2 to 1, this quantity then is S1 minus S2. In other words, if I do the cycle 1 to 2 and 2 to 1, I have an integral that's 0. So why exactly is that a state property? It is a state property only if you are in a reversible cycle, because then by necessity you have a state here and a state there and a state there and a state here, so that your integral has to be 0, and therefore the things are defined only at 1 and at 2. That quantity is entropy. And for the reversible cycle, the change in entropy over the cycle, 1 to 2 and 2 back to 1, is 0. Because the sum of this and that, of course, sums to 0. So this is why the entropy change in a reversible cycle, only in the reversible cycle, is defined only at states 1 and 2, and you don't need to know the path, because in fact the path is uniquely defined. It's the path of the reversible transformation. Now, what do we do when the path is not the reversible transformation, the path of the reversible transformation? So you go from 1 to 2, and then if you go through an irreversible path from 1 to 2, you can't use that equation. This is not correctly defined, and this would then not be an equation of state. Because we want an equation of state. We want the equation of state because we want to be able to tabulate it. So we can only define it for the reversible quantity. So we have a recipe as to what you should do when you have to deal with an irreversible transformation. What you have to do is find the reversible path that would be between the same two states. So if you want to know the entropy change here, well, you can only define the entropy as an equation of state at 1 and 2 if this is the reversible path. So if you have to deal with this cycle or this transformation, go find what it is for the reversible path. So you have to find the reversible path. Then you call the change in entropy over the reversible path the integral between 1 and 2 of this quantity Q over T over that path. And so this is all you can do. For an irreversible process, you can only define it for the reversible process and then later correct that for the effects of the irreversibilities. Okay, so what do we do to correct this with the effect of irreversibility? So let me take here a cycle. I start here, I go here, I go here, I go back there, and I go back there, and it's reversible. So if this is the blue is the reversible path, then the integral of the reversible path is 0. And that you can then define the entropy at each of these states separately. Now, if you have this irreversible path, we use the Clausius inequality to know that the real integral will be negative. So what do? Well, we say that if you are going to go through this irreversible path here, you're going to have a ds that's 0, but it will be the entropy. Well, it's not an entropy. It will be this integral of q over t for the irreversible path plus a correction factor, which will then make it possible for you to write this as ds is q over t over the reversible path plus the sigma. And that means that if I have this transformation and I apply it, so this is basically the entropy that is generated by the irreversibilities. If I now apply the Clausius inequality to that, indeed, I can get this to be negative, even though that has to be 0, because it's equation state, by having a certain amount of irreversible entropy to be positive. So now you have a total entropy function, that is this reversible entropy, well-defined as the integral of q over t over the reversible cycle, plus the entropy generated by the irreversibilities, and that is actually the function that has to be maximized as the system goes to equilibrium. This was the Fermi definition of entropy. So let me summarize this once again, because it's quite complicated. We define entropies as equations of states, but they can only be defined if we know the reverse and derived, if we know the reversible path that gets us between the different states. So we know then that the integral of a dq over t reversible has to be 0. We can call then ds over that whole cycle, and that is the integral of the cycle has to be 0. Now, if the cycle is irreversible, we still want to be able to define ds as being 0 for the cycle. ds is 0 for the cycle. So we want to define capital S as an equation of state by definition. But we have to deal with this integral over q over t for the irreversible cycle, which of course has to be negative from the Clausius inequality. So we have to correct for it by separately adding a term that is the entropy generated by the irreversibilities, so that this term compensates that term so that we can then define S as an equation of state. So that means that since this has to be negative for irreversible processes, the correction that takes into account the entropy of the irreversibilities must be positive. It must be positive. The more you have irreversibilities, the more it is positive. And therefore, you have a function that defines the nature of the irreversibility, and you know that that is a function that is going to be maximized as the system tends to equilibrium. This is why Fermi defined entropy as the function that gets maximized as a system goes to equilibrium. Now, let's define ideal Carnot cycles, because let's go back. In the ideal Carnot cycle, the system is completely reversible. Every step is reversible. So the blue line here would be a Carnot cycle. The red one certainly not. Can't be anything. Has therefore an efficiency that's lower than the Carnot efficiency. Let me give you a few examples of Carnot cycles. We will revisit the theory again later, but let's just go over a few examples. Example 1 here would be an ideal gas that we will put in a cylinder assembly with a piston. And the Carnot cycle now starts with a gas, the piston high up, the gas in there, and we compress the cycle from 1 to 2, and we compress it adiabatically. In other words, the wall around the cycle is perfectly thermally insulating. Perfectly thermally insulating means there's no heat exchange in the cycle, and the work from here to here is done on the fluid, so it's negative. So let's go here from this state 1, which is with this piston out, to this state 2, which is this gas compressed. The pressure has gone up, the volume has gone down from here to here, and we have actually done work on the fluid, but we have not changed the heat. We do this very, very slowly, because if we don't do this very slowly, we will heat up the system by the compression itself, and that would be heat that we don't want to consider. So the process is very slow, so the heat transfer between reservoirs and fluid happens over infinitesimally small temperature gradients. You don't change. Okay, now you're going to be taking a system and you touch it, you bring it from here to a hot reservoir. And now you let the heat penetrate the system nice and slowly again to have the transformation locally quasi-equilibrium every time. So you add heat to that thing. As you add heat to that thing, the system will expand, but you also make sure that the temperature is constant. So you expand at a constant temperature. It's an isothermal expansion. So we add heat at a constant temperature, TH. So we were here at 2, and we expand. So we are at a constant temperature, TH. This is an isotherm for the ideal gas in the PV diagram, and the volume goes up, but the pressure is the same. Now, sorry, the temperature is the same. Both pressure and volume change. Pressure comes down, volume goes up, but the temperature is the same. Okay, so now we're all the way there, and we now expand it adiabatically. In other words, we cut this heat off, we insulate it, and we let it essentially cool down from T hot to T cold. And then, so this gas is expanded Q through 3. Well, I got that wrong. We let the gas do work between 2 and 3, but we do not touch the heat on it. So W34, we're going to 3 to 4. 3 to 4 is we put it insulating, we have heat into it, and we let it expand. So it does work, but then we didn't add any heat. That is 3 to 4. And then heat, well, then we connect it to the cold reservoir, and the heat 4 to 1 is negative, drains from the system, so the volume now decreases, but isothermally at T cold. So this is a system that has gone adiabatic, isothermal, adiabatic, isothermal. That is an ideal a Carnot cycle. That has an efficiency that is only the Q hot over the Q cold. The net work done is W34 minus W12, and W12 is a compression, W34 is an expansion that does work, where the system does work on the outside. And the efficiency, W34 over W minus W12 over the heat that you have paid for it, QH, is QC over QH, which is 1 over minus TC over TH, which is a Tamax. Here is a steam cycle, which is also a Carnot cycle. So this is an ideal Carnot cycle. Let's start here with steam, pure steam, that comes straight out of a boiler. In the boiler, the steam has received a certain amount of heat, QH, that transformed it from liquid to vapor. So Q41 converts high pressure water to steam, but it does all of this at a constant temperature TH, the boiling temperature at that particular pressure. So we start here at 4 with saturated water. We get it to saturated steam at 1, and that we did by adding QH to the system. Now we send the saturated steam through a turbine where we let it expand and do work on the shaft of the turbine. So that cools it down. You start from a saturated steam 1 to a point number 2, doing work, which is in the PV diagram, the integral under 1 and 2. That is this work. This happens without losing heat through heat losses through the turbine. So it happens adiabatically. So There are no heat losses to a turbine. It's perfectly thermally insulated. The entire change in pressure comes from producing work. Now we go from 2 to 3 in something that condenses the steam. So we have the steam had a certain amount of quality, and we keep it at that temperature T2. Isothermally, we bring it from 3 to 2. That drains the heat Q23 from the system at constant temperature Tc in this condenser. So that is this quantity Qc out here. And then we feed it back through a pump. So here we have water, and we compress that water from 3 to 4. So we bring the pressure up and the temperature up from 3 to 4 by adding work to it. So again, the pump is adiabatic. There is no exchange of heat there, and we have put work into the system. So once again, we have an isothermal system at the boiler. We have an adiabatic system at the turbine. We have an isothermal system at the condenser. We have an adiabatic system at the turbine. The only thing that changes is the heat in and the heat out. Then the turbine produces work, but the pump takes work, but less work than the turbine has produced. So the difference in work between work out and work in is the net work. Divide that by Q hot, that is your efficiency. We know that because the cycle is extremely slow, it is completely irreversible. So we have the Carnot efficiency, QC over Q hot. We know, therefore, that it is 1 minus QC minus TC over T hot, and that is eta max. So you see, characteristic of a Carnot cycle is an isothermal transformation, an adiabatic transformation, an isothermal transformation, and an adiabatic transformation. We can make reversible thermodynamic cycles using pure electrons. So this thermoelectricity, this is not in your book, but this is what I do in research mode. So bear with me for 3 minutes. You have a solid that is here filled with electrons. Any metal is filled with free electrons that just can behave essentially like ideal gas particles. So your volume is constant. Your pressure of electrons in that system is constant. Your number of electrons is constant. If I now heat up one side and cool down the other side, I know that I'm going to have to keep PV as NIT. So if T is hotter here than there, well, there will be more electrons here than there. Now, because there are more electrons, this side becomes charged positively, and I therefore have a voltage that appears across that system. The ratio, or an electric field, the ratio of the voltage over the temperature difference, or the ratio of the electric field over the temperature gradient, is what's called the thermal power of the system, or the Seebeck coefficient of the thermal power. I can demonstrate, but it would take me an hour in a graduate level class, that in fact the Seebeck coefficient, or this thermoelectric power, is nothing but the delta Q over T divided by E. In other words, the entropy of the electrons divided by E, which is the electron charge. All right. So now if you take a thermocouple or a Peltier cooler, which you can buy anywhere, you have seen thermocouples, you have a wire that's N-type and a wire that's P-type. Well, the wire that's N-type is filled with electrons. The wire that's P-type is filled with holes. Let's heat that up, and if my animation went right, my electrons would come on this side, my holes would come on this side. So this becomes more positive than that. That is more positive than this, which is most negative. So I will now generate a current that will go out of my system. So my electrons will go this way, my current will go in the opposite direction. My electrons go this way, my current goes that way. But if you look closely, because this Seebeck coefficient, the ratio, the voltage per temperature difference, is an entropy, if that Seebeck coefficient is constant, we have an isentropic transformation here. Here we have another value of entropy, which is another value of the Seebeck coefficient of my electrons in this one. But if it is constant with temperature, This also is an isentropic transformation. Of course, on this side, the isentropic transformation is here, and on this side, the isentropic transformation is there vis-a-vis an arbitrary axis for Seebeck coefficient or entropies. Now, this is an isothermal transformation, and that to the load resistance is also an isothermal transformation. So we have, as far as the transformation goes, if I follow the electron, a heating up, an isotherm, a cooling down, and an isotherm, which corresponds simply to the carrying of the electron here. So this is an isentrope isotherm, isentrope isotherm, isentrope isotherm, isentrope isotherm. I have a Carnot cycle. The efficiency in a purely reversible thermodynamics, the efficiency of a thermoelectric device is actually the Carnot efficiency. Now, of course, that is not true in practice at all. There are many irreversibilities in the real world, and we will get to that in the next lecture.